My name is Tuszynski. I'm a professor of physics, but also oncology here at the U of A. And I haven't been teaching except for this course in the past decade or so. But this year is very different, and I have to say very interesting, because in the space of 4 months I've taught in 4 different countries. Italy, France, Canada, and next month in Poland.
Wow.
And also I'm giving a public lecture in Milan on quantum biology, so this is the warm-up.
Excellent.
Anyway, this topic combines my 2 major interests, namely quantum physics and molecular biology. And in this title you see that there's also a hint of quantum medicine. I think we're not there yet, for sure, but we can think about it, as this is the future of medicine. The question is how far into the future we have to look to find a possibility for quantum medicine. But today, so there'll be 3 lectures, as you know. We have changed the schedule a bit. So they will be in succession. Today, next Tuesday, and next Thursday we'll cover the topic. And today I will put everybody more or less on the same page. I don't know where you come from scientifically, but I prepared a talk which is generally accessible to all, I hope. Maybe I'll just ask you by a show of hands if anybody here has a background in physics. Wow, okay, so good. That means I will not be wasting your time today. Welcome, please come.
There are more chairs in the corner if you want to pull some out.
And anybody with a background in science, not medicine, but science. So it's half of the crowd, more or less, maybe more. Okay, very good. So I would imagine biology, chemistry, maybe math, comp sci, this kind of thing. Okay, so we'll start with actually prehistory. As I like to emphasize, physics is the oldest branch of science, and some people think it's the only branch of science. Started with Galileo and Newton about 350 years ago. But when you say quantum, and we'll be talking about quantum, this is in contradistinction to classical physics. Classical, like classical music, classical physics, quantum physics, or rock music, let's say, or modern. So quantum physics rocks. But what is classical physics? So these are the main building blocks, fundamental parts of physics. Classical mechanics, going back to Newton, and other names. So I bolded the main names for each of these building blocks, edifices of physical sciences. Newton, of course, created mechanics, optics, calculus, and other, not really that small in comparison, but Lagrange, Hamilton in particular, because Newtonian mechanics is actually for kids. For real physicists, use Hamiltonian mechanics or Lagrangian mechanics. And others, but we have no time to go into deep history, just to give you some buzzwords. So classical mechanics, electromagnetism, so electricity and magnetism combined to fused into electromagnetism, and later on to electrodynamics. All about charges, stationary moving charges. Started actually with experiments by Ampere, Faraday, Ohm, and put together into one beautifully elegant field of physics by Maxwell, James Clerk Maxwell. And then we move on to 19th century. So these were discoveries made in 18th century. 19th century was dominated by the Industrial Revolution, which put pressure on scientists as well as engineers to come up with better solutions to the demands of transportation, fabrication, manufacturing, etc. And thermodynamics was the field that grew out of these pressures. And here we have, James Watt and Carnot, Thomson, Clausius, these names. And Gibbs really the first American, or North American scientist of note. Not the only one. These days actually it's the opposite, but in those days it was dominated by European science. And Gibbs was the first really major American physicist. Gibbs put thermodynamics under some very logical and complete mathematical framework, so that classical thermodynamics is really a complete science, just like classical mechanics. And then things got a little bit messy towards the end of the 19th century with the development of statistical mechanics. Statistical mechanics is a combination of statistics and thermodynamics, actually. So some people call it statistical thermodynamics. And it is also important in the context of quantum physics, as we will come to appreciate in a few minutes. That's why I'm mentioning it here. These names, Nernst, Helmholtz, and especially Boltzmann. Boltzmann was an Austrian physicist who was really one of the first revolutionaries. He came up with ideas which were completely out of the box and was hounded out of physics, more or less, by his contemporaries to the point of committing suicide, which is very sad but true. And now, Boltzmann's ideas seem to be of historical importance because they transcend physics, actually. Boltzmannian statistics can be applied to such fields as economics, even politics, sociology, biology, the concept of entropy in particular. Even our illustrious Prime Minister used entropy recently, Justin Trudeau, in one of his speeches, but maybe I should mention that. Not to put Boltzmann in disrepute. So much of it, physics, as I said, physics is the oldest branch of science and the most mature, but wouldn't be possible without mathematics. And this is actually indispensable if you want to understand the birth of quantum mechanics, because without the advances of mathematics about a century before, it wouldn't be possible to come up with any quantum concepts as we know them today. So at the time of the dawn of quantum mechanics, which is early 20th century, there were a lot of very sophisticated mathematical tools available already. And these physicists, as you will see, that their faces and names were very familiar with these tools. So calculus, of course, going back to Newton and Leibniz and others. But in addition, and especially partial and ordinary differential equations, which were developed by Laplace, Lagrange, and many other mathematicians at the turn of 18th and 19th centuries. Functional analysis actually is the toolbox of quantum physics. Functional analysis is the use of operators, Hermitian operators. So Hermite was the French mathematician who developed this field, among many others. Linear algebra, because in the end, as you will see, quantum physics solves problems. And you have to have these mathematical tools to be able to solve quantitative problems. There is no more precise field of human knowledge than quantum mechanics. Quantum mechanics allows you to find values for fundamental constants with a precision to, let's say, 20 digits, something like this. So that requires incredibly precise tools. Tensor algebra, theory of distributions, which was later on used by people like Dirac, with the famous Dirac function, with Dirac distribution, and the theory of probability, because as opposed to classical physics, which is very deterministic, that is, follows the famous dictum of Laplace. Laplace was so confident that he stated that if you give me the initial conditions of all particles in the universe, I'll be able to predict the future of the universe, which is, as we know today, blatantly silly, but at the time it was very convincing because of the deterministic nature of classical mechanics. Classical mechanics solves ordinary differential equations with initial conditions, or partial, but mainly ordinary, and leaves no room for probability, And probability, which is, in other words, uncertainty about the outcome of some experiment or measurement, is part and parcel of quantum mechanics. Okay, so that gives you the sort of historical background to the beginning of the quantum era, which coincidentally started in the year 1900 precisely. But in 1894, which is 6 years before the beginning of the most incredible scientific revolution known to mankind, peoplekind, Albert Michelson, a Nobel laureate, actually, very important name, although probably nobody knows about Albert Michelson, because Michelson morally measured the velocity, speed of light, which was the piece of information that Einstein used in developing special theory of relativity. So, yeah, this guy was, yeah, was very smart, but he said, and by the way, this was attributed incorrectly to Lord Kelvin, but Michelson said, it seems probable that most of the grand underlying principles have been firmly established. The future truth of physical sciences are to be looked in this 6th decimal place. In other words, there's nothing to be discovered. He stated that what's left is engineering, as physics is finished in 1894. And here we are today, 2019, a century after quantum mechanics was introduced into science. We still don't understand quantum mechanics completely. So, so much for bombastic statements. So, just to give you this sort of landscape, because quantum mechanics was not the only thing that was happening at the time, and is happening now. The 20th century was a century of scientific revolutions, and that slide is one semester course, by the way. But just to give you a few bullets, so special theoretical relativity, which I mentioned, Albert Einstein single-handedly introduced this concept of space-time continuum. And then general theoretical relativity by Einstein also, same guy who actually didn't get Nobel Prizes for these things, something else that you'll see in a minute. And then quantum mechanics, so these are the names of the players. I was actually trying to prepare a talk today about this as a play. So the actors, we see have the main actors in this play: Max Planck, Erwin Schrödinger, Werner Heisenberg, Wolfgang Pauli, Paul Adrian Dirac, and others. But you know, so these days, when you hear about Nobel Prize being awarded in November every year to various people in various fields, by December you forget who got the Nobel Prize for what, right? But these guys got Nobel Prizes for things that humanity will remember forever, because these are so fundamental. And this all happened within a span of 30 years or so, which is truly amazing. And by the way, as a side note, I always wonder about these bursts of geniuses on the human landscape, you know, like the Renaissance in Italy and the Baroque musicians in France and Italy. But this is the group of people that created quantum mechanics. And also they were bunched in time and in space, more or less. For some strange reason, they came, most of them, not all, but came from the German-speaking part of Europe, either Germany, like Heidelberg, Göttingen, or Switzerland, Zurich typically, or Austria. So Dirac was English, by the way, but he was half Swiss. So there was something Germanic in it. Okay, and then so that gave rise to proliferation of quantum ideas in other fields. I want to mention quantum chemistry. Today, chemistry cannot be understood without quantum mechanics. We cannot really understand chemical bonds without the concept of wave functions, orbitals, molecular orbitals, atomic orbitals. And we take it for granted, right, that chemistry is really quantum physics. Although maybe people don't say it like that. Especially chemists will not tell you that. And for this reason, you know, you can actually reduce things to this smallest components, and you can say that chemistry is really quantum physics, and biochemistry is really chemistry of biological molecules, and biochemistry is also quantum physics, really. Then you can say biology is really biochemistry with the addition of fuel, so and metabolism, then of course biology by definition must be quantum physics. That's a sleight of hand, I would say. I'll try to make a stronger effort than this, but you can argue like that. Quantum physics did not stop in 1927. It's still evolving. As you may have heard, these days actually there's a lot of talk about quantum computing. Right? It's application of quantum ideas to computers, building quantum computers. But there's actually deeper conceptual development that occurred starting from the 1940s up to even today, quantum field theory, and eventually, grand unified theory. So understanding the foundational basis of all matter requires going beyond quantum mechanics. Quantum mechanics, as you will see, is not sufficient to understand how elementary particles are built. You have to add to it concepts of fields. But again, that's beyond the scope of this course. I'm just giving you some lay of the land, so to speak. I don't want to forget, that in 20th century we also experienced an incredible revolution in biology by the discovery of the genetic role of DNA and the structure of the DNA, double helix, the whole molecular biology. But, all right, we are here. I've added to it a hint of quantum biology. We're not there yet. I don't want to oversell the point. There are some examples, but of biological processes which are undeniably based on quantum physics. But I want to, in this talk today, emphasize one thing, that quantum physics began exactly the same way. Namely, at the turn of 19th and 20th centuries, there were simply a few examples that didn't quite fit into the story of classical physics. They're difficult to explain, impossible to explain really, and honestly, physicists were perplexed, and in some cases actually acted against their own conviction, including Max Planck, to introduce new ideas that were not consistent with the past. But you had to do it to explain what was observed. Physics, like biology, is an empirical science. It is really based on observations, and if you observe something, you try to explain it, and then if your explanation is not good enough, then you have to revise it and refine it. But actually, another topic for a separate lecture, the scientific method. What is the scientific method? I don't have the time again, but I encourage you to look it up on YouTube, and Richard Feynman, one of the greatest physicists of the 20th century, has a beautiful lecture on the scientific method, which, by the way, came completely opposite to the medical method.
Yes.
You know, right? Because this scientific method is searching for not a validation of your prediction, but falsification of your prediction. That's how science works. You try to find where your theory or hypothesis is going wrong, and it will always go wrong because we have limited brains, and science is infinite. So we're always on the path to improvement. In medicine, you always try to eliminate all the possible diagnoses in the differential diagnosis protocol, let's say, and end up with one, which is the one that explains the symptoms. But that's not how science works. Okay, so this is the timeline for the development of quantum revolution. As I mentioned to you, 1900 starts with, so 20th century started with a Big Bang. Max Planck introduced the idea of energy quantization, and this is the word we use, quantum physics, due to quantization. That means energy is not a continuum, a parameter with a continuum of values, but is discrete, quantized. Okay, so that's the origin of the word. Although, yeah, we need to discuss a bit deeper what energy quantization means and under what conditions. This was used to explain many years of observations of the so-called black body radiation. I'll show you that in a few minutes. A short 5 years later, Einstein used the concept that Max Planck introduced and explained the photoelectric effect, which is commonplace these days. If you go into any major airport's washroom, you will notice lights lighting up and the urinals flashing down automatically because of the photoreceptors. So the photoelectric effect is behind all of this. Then 1913, Niels Bohr from Copenhagen, importantly because Copenhagen is the birthplace of the so-called Copenhagen interpretation of quantum mechanics. That is interpretation based on probabilities rather than deterministic predictions, in a major deviation from the scientific thought of the previous era. So Niels Bohr explained emission and absorption spectra of atoms, hydrogen, helium, neon, and others, by using energy quantization for electrons in an atomic model, which was called the planetary or solar planetary model of the atom. 1924, and by the way, you know, if I had a semester to teach this course, we would have a lot of fun because every person listed here is quite a character. And Louis de Broglie, by the way, he was a count. He was an aristocrat in France, and he basically enjoyed himself doing physics. And as a byproduct, without actually finishing any physical degrees, he got a Nobel Prize, just like that. So kind of fun era, right? As a hobby, you get a Nobel Prize. So he introduced something very important, and again, completely revolutionary. Until then, in mechanics, you had particles, right? Billiard balls hitting each other, colliding. In electromagnetism, you had waves, and also waves in optics, in acoustics, acoustical waves. But he said, well, actually, in quantum mechanics, there is no distinction between the two. Every particle is a wave, and every wave is a particle, depending on how you look at it. So that's called the wave-particle duality. It's again, today, it's sort of a big deal. But then it was really a big deal because it changes completely the concept of the world. Nothing is hard. Nothing is precisely defined in terms of shape. If you think about particles, you think about shapes, but waves don't have shape. They propagate, they spread, and they're everywhere. So he's introduced this concept that every particle is a wave, really. And every wave can behave like a particle. In fact, light doesn't have mass, but has momentum and energy, just like particles do. Okay, then the next group of people went into sort of abstract territory, deep water. 1927, Heisenberg formulated the uncertainty principle, which actually kind of, I missed these two. I'll come back in a second. But the uncertainty principle is in a way consistent with this wave-particle duality because it tells you that you cannot simultaneously measure two complementary properties of an quantum object, such as position and velocity. You cannot simultaneously know where a particle is and how fast it's moving. Either or both with some uncertainty. But you cannot say, I know precisely where the electron is and how fast it's moving. You cannot do that. So that's again, a complete departure from determinism, and also giving a philosophical impact on our perception of the world. That, back to Laplace, remember Simon Laplace, de Laplace? He said that, yeah, we can predict everything once we give me the conditions of the particles and position, momenta. Well, no way, Jose, you cannot do this, even for a single particle, let alone the universe. But back to Heisenberg and Schrödinger. Heisenberg, and by the way, every name I mention today is a Nobel Prize winner. With one exception, actually. John von Neumann. John von Neumann, who is the grandfather of computing and computer science, and never got a Nobel Prize. So, but everybody else did. So here we have Heisenberg and Schrödinger. So they formalized quantum mechanics into two equivalent mathematical theories. So they introduced equations such as Newton's equations for classical mechanics. They did not derived, proposed, because you cannot derive it. They proposed equations which describe quantum nature of matter. One is the Heisenberg equation for so-called operators. Operators, as you will see in a few minutes, represent physical properties. So this is about the evolution of physical matter. If I say a given number of particles are localized roughly here with a particular energy, what will the system look like 10 seconds from now, a million seconds from now, or a billion seconds from now, but not, emphasis, not precisely, probabilistically. What is the probability distribution of this happening? Just like, let's say, in the run-up to elections, pollsters give you predictions what will happen. Liberals will win, or with this probability, conservative. This is like in quantum mechanics. That's what we do. We make predictions. With this probability, something like that will happen, something else with another probability. So that's the Heisenberg equation of motion for operators, and the Schrödinger equation, the famous Schrödinger equation, is for wave functions or probability distributions. And I will have to introduce the wave function to you because it's an alien concept if you're another physicist. And finally, Dirac actually made another major step. So remember when I talked about scientific revolutions, one of the revolutions that occurred at the same time was special relativity, which means that even classical mechanics has limitations when particles move at very large speeds, close to the speed of light. Then Newton's equations are no longer valid, even in the classical case. You have to rewrite this in so-called relativistically invariant way. So what Dirac did was he actually formulated quantum mechanics consistently with the special theory of relativity. In other words, for particles like electrons and protons, neutrons, that may be moving at a fast speed. And actually, even in atoms and molecules, they are moving at a large enough speed that you can see these effects taking place. Okay. John von Neumann formulated in a very elegant way, which is including interactions. And then from 1940 on, and I will stop here, this historical thing, because it gets really hairy, and I would have to start writing a lot of complicated equations that take up, one slide or more. But these three gentlemen, Feynman, Schwinger, and Tomonaga, introduced quantum electrodynamics, which basically is the fusion of relativistic quantum mechanics with electromagnetism. And then that served as a prototype for quantum field theory, and even today, things like the supersymmetry and gauge field theories, all of it is a continuation of that humongous effort going back to 1940 or so. Feynman was also a very interesting character. Loved to play the drums in spare time, and spent a lot of time on the beach in Rio. But okay. So this is the galaxy of the greatest galaxy of geniuses ever assembled on this planet in one place at the same time. In Brussels, Belgium, in 1927, Hotel Metropole, actually, which I had the pleasure of visiting. I spent a year in Belgium on sabbatical and couldn't resist going to this hotel. So you can see here many of the names I mentioned: Max Planck here, Marie Curie, Albert Einstein, and Dirac, Sommerfeld, Schrödinger, Pauli, and Heisenberg, and others I have to look up. I know in looking from the perspective of 2019, you see a lot of old white men, but there's one lady. So And she was the only one who got 2 Nobel Prizes. Everybody else got only 1. So, anyway, that was the beginning of a march to equality. Hmm?
Still is like that.
That's a topic for another conversation. But no, but it's very. So the importance, I think there were 2 of these or 3, I don't remember, 26 and 27. These conferences brought everybody who was anybody in this field to discuss how to unify it, to make a consistent picture, because there are a lot of different interpretations and a lot of different experiments to work on. It looks scattered. And so they discussed and decided on the shape of quantum mechanics as a consistent theory of matter, or the universe, in fact. So let me just summarize. I kind of hinted at some of the properties of quantum physics compared to classical, but I'll try to summarize and then give you some examples, because all of this came as a result of 5 or 6 experiments, only 5 or 6 experiments which did not agree with the understanding of matter at the time. But the main thing is that quantum mechanics, at least at first, was obsessed with microscopic objects, very small, tiny particles, right? Or atoms. Atoms and things below an atom, so electrons, protons, neutrons, and then later on more exotic things like muons, gluons, and Higgs bosons. Yeah, so it's microscopic. Classical physics typically is limited to macroscopic things, like this table, this desk, a car, ping pong ball. But things get blurry, so at first it was like that. Today I wouldn't say that. Okay, so this is Bach. But there are, today, not then, but today, there are many examples of macroscopic effects which are quantum mechanical. And these macroscopic quantum effects can be found in superfluids. So these are very low temperature helium-3, helium-4 fluids which flow without viscosity due to quantum effects, condensation. So, superconductors, another example of macroscopic objects which have conductivity without resistance. So not only that, but some other properties, but mainly no resistance. Something that everybody knows today is a absolutely quantum effect, lasers, laser action. Laser action is because of the discrete quantum levels of electrons in specifically designed systems, which emit photons, or quanta of light, with precisely the same frequency and in phase. So lasers, today of course used as laser pointers, as barcode scanners, everywhere we have lasers, right? This is unashamedly a quantum phenomenon. And if somebody asks you, where do you see quantum? Well, go to the nearest supermarket and scan the product, and you have a quantum effect, laser action. But even things which are very commonplace, more than lasers, have underlying quantum dynamics, which is crystals, all crystals. If you have a crystal lattice or structure, it has organized atoms in a regular position. Say a cubic crystal. I don't know, I'm not very good at drawing, but you get the picture. You have atoms positioned regularly in a lattice structure, and so on. So when you look at it from the point of view of statics, there's nothing special. Okay, they sit there. But if you start understanding and analyzing their motion, they move around their equilibrium position. Nothing is stationary, not even at 0 Kelvin. So these oscillations of atoms are in a concert. In other words, they like in a synchrony, they move around their equilibrium positions and create waves called phonons, or lattice vibrations, should not be confused with photons. Photons are quanta of light. Phonons are quanta of lattice vibrations. Alright. So almost every regular solid generates quantum excitations. And to see it, you have to measure something called the specific heat of a solid. I'll come back to it a bit later because it's very important, as it really has a close analogy in biology. Both photons and phonons have, I'll just say now, and later on I'll elaborate on this. So photons are quanta of light, electromagnetic radiation in general, not necessarily visible light. And phonons are vibrations, so vibrations of a solid, quanta of vibrations in a solid. So that's physics, right? In next week, I will try to convince you that there is something completely parallel in biology. So there are photons and quantum absorption of photons in biological systems, in the plants, in chlorophyll, and this is in photosynthesis. Photosynthesis is perhaps the first fully quantum mechanically described mechanism in biology. So there's a connection here between photons and actually the photoelectric effect that Einstein got the Nobel Prize for, photoelectric effect, and photosynthesis. And then phonons, or lattice vibrations, as I will try to explain next week, which are quantized, and that signature of quantization is seen in specific heat measurements of solids, beyond the shadow of the doubt. Actually, also awarded the Nobel Prize to Debye in around 1940 something. So this is analogous to the scaling laws of metabolism, human or actually animal metabolism across the species. So metabolic enzymes exhibit hallmarks of quantum physics. That's an advertisement or commercial for the next lecture. All right, so there are two major objections, by the way, to quantum effects beyond microscopic physics at very low temperatures. The first objection is size. The bigger things don't require quantum. We have examples contrary to that. Superfluids, superconductors, lasers, even solids, all have hallmarks of quantum physics, even at large sizes, infinite, in fact, sizes. And second is the argument of temperature. That temperature somehow kills quantum effects because quantum effects are subtle. If you heat up something, then all goes down the drain. But that may not necessarily be so, as is the case with photosynthesis. Photosynthesis occurs at room temperature or 40 Celsius, high temperatures. So, and superconductors, by the way, we have something more recent called high temperature superconductors discovered in 1986 by Bednorz and Müller in Zurich, and they got the Nobel Prize, of course. And these, today, they're not at room temperature yet, but not too far from room temperature. So maybe Siberian temperatures, but not room temperatures. So in other words, we're not technologically advanced to see it at room temperature, but there is no reason to doubt that this may one day become room temperature. All right. So that's the argument for quantum physics beyond physics. And then I just recapitulate some of the things that I mentioned to you. Wave-particle duality as the major differences from classical to quantum. Introduction of probability theory, so instead of knowing precisely where things are and how fast they move or what sort of energy they have, even the question of at what time point this happened. So the uncertainty principle that I mentioned, the Heisenberg uncertainty principle that I mentioned to you, tells you that you cannot know for sure whether something is here and how fast it is moving, but also what energy it has and when it was that it had this energy. So energy and time are so-called complementary properties, physical properties, observables. And then the third thing is really philosophically very deep. And some people think that, I mean, take it to the extreme. In quantum mechanics, there is no objective measurement. It's not possible to objectively determine anything at all in quantum mechanics. Because every measurement, even the most subtle, the most precise measurement, is always disturbing the system that you measure. Whether you use a single photon or a single electron or some other tiny particle, you will always affect the state of the system that you're trying to analyze. So that's the observer problem. In classical physics, as you may know, this is the system I study. Let's say a bucket of water that you heat up or something, and you make an objective measurement. But in quantum mechanics, there is no separation between the observer and the system. So it's very difficult conceptually, and so the extreme that people go to would be that they say that there is no reality outside of the subjective experience. In other words, the universe doesn't exist without the active observer observing it. It sounds funny, but you know, you can engage in this kind of philosophical debate whether something exists if you don't perceive it, or measure it, or observe it. Okay, so I mentioned quantization of energies. That's the basis. So now a few slides about the origin. The reason that I'm bringing this up, and it's a bit more technical, but not really that much, is that it really is similar to the situation today in biology. Biology at the turn of 20th and 21st century has exploded in terms of data collection. There's so much data, there's so much information about biological systems, more and more precise, admittedly, but very little conceptual framework. There's very little that you can say, this is the theory of living systems. Can anybody tell me what is the theory of living systems other than Darwinian adaptation or selection? Not much, if anything. So physics was in a slightly better position because there were theories already, but these experiments that I'm going to go over quickly, they kind of undermine these theories. And the first one was, this is the power measured of emitted radiation from objects at different temperatures. It's called black body radiation. And the x-axis shows you the wavelength in micrometers, and you have different temperatures. So the higher the temperature, the lower the peak wavelength, and this was given by this formula called Wien's law. So experimentalists were measuring this and assembling data, and then they asked the theoreticians to tell me how it works. And people thought that, okay, it's simple, just, every piece of matter is composed of oscillating parts, and these oscillating parts emit radiation, and depending on the frequency of oscillation, you get different emission spectrum. And you do some sort of statistical averaging, and they get nothing out of it that made any sense. So this is what Max Planck proposed. He said, actually, it's not like that. Yes, there are some oscillating parts, so atoms have oscillations, and they emit electromagnetic radiation, but they cannot emit at any frequency. They emit at packets with a given energy value called energy quanta. So this is the formula, Planck's radiation law. But by the way, you'll have access to the slides if you want and go deeper. And there are two remarkable things about it, at least two. The first one is energy emitted by solids, let's say, is proportional to the frequency. So that was new, that frequency of oscillation scales energies. If something oscillates rapidly, it has more energy. Slow oscillations have less energy, which actually is quite interesting. And think about it, it sets the tone for understanding biological systems. If you think about this, because in biology you have oscillations. Every living system has hierarchy of oscillations, right? And typically, the smaller the part of the biological system, let's say ATPase, the faster the oscillation. If you look at the whole body, the human body, we have typically circadian. So you sleep at night and you wake up in the morning. This is the slowest way, right? But when you look at our biochemistry and physiology, you see much faster processes taking place, right? So it's a bit like this. So the smaller the object, the higher the frequency, the bigger, the lower the frequency in different time scales. But this is the famous Planck formula. Energy is proportional to frequency, and he threw in a constant called the Planck constant, which is one of the fundamental constants of nature. There's no explanation for it. There's no derivation of it. There's no rhyme or reason that this is it. This is the constant the universe that we live in chose to use. So you can say it's God-given if you believe in God, but if you don't believe in God, it's just one of those mysteries of the planet, not of the planet, universe. Okay, so that's the Planck constant. Is one of the most precisely known parameters to humans. Okay, so two things, the Planck constant and the energy-frequency relationship. So that was, and then this is the guy that I like to talk about, Albert Einstein. So that was the second experiment that kind of shattered the foundation of physics at the time. The photoelectric effect, you shine light on a glass-encased tube with electrodes, an emitter plate, collector plate connected to a battery, and an ammeter measure the current. And depending on the wavelength of light or the color of light, you do or you don't have any current flowing. And that was the nature of the thought, breaking or forming a circuit, depending on. And it was actually the higher the frequency, but from a threshold value, the greater the current. And so that's the setting of the experiment, and Einstein used this Planck formula and explained it as follows. Maybe too many words here. Basically, electrons which sit on the collector plate, or the emitter plate, get ejected from the plate if they get enough energy. So that's basically going deeper into this. An electron is sitting here in order to start flowing from one end of the sorry, can you see it? Electrons get ejected from the plate, and these electrons go to the conduction, or actually they get freed from the metal surface. So this is valence, they sit, and then they get ejected, provided the energy of light that is delivered, so this is light, exceeds the so-called work function, which is the gap, energy gap. So there's an energy gap that's discrete value. So that's called delta E. So if H nu is greater or equal than delta E, you have a current. If it's less there's no current. Current? No current. That gives you a limit on the frequency or wavelength, opposite to it. No current. Simple explanation, but revolutionary because assume that you have to overcome a finite energy gap from the ionization, basically. Okay, that's the photo, and Einstein got a Nobel Prize for it, and he actually, another anecdote, you may or may not know, he never got a single dollar out of it. And Einstein's Nobel Prize was one of the smallest ever. He got about, in today's currency, about $315,000. Average is about $1 million or so. And he he gave all of it away to his ex-wife, because when they divorced, in the settlement, he said that in the unlikely event I get a Nobel Prize, it'll be given to you so you can buy a house for you and your son in Zurich. Sad. That's true. Well, maybe not. He was a good guy. So yeah, that's basically it. So you see here, red is long wavelength but low frequency, so less energy than blue. So in this case, red light will not eject any electrons from the surface. Green starts ejecting when you have blue. It's the highest energy invisible spectrum. Not only will eject the electron, but it will also give it, the excess energy will be turned into kinetic energy. They will start flowing very rapidly. And then the greater the intensity, the more the rays of light, the more photons, and therefore you can increase the current flow in terms of numbers of electrons. Okay, that's basically the explanation of the photoelectric effect, which we use in light switches and sensors and light sensors and whatnot. And just a list of other experiments which were piling up. The Compton effect, it showed that electrons and photons behave both like particles. And that's the Broglie duality aspect. So if you had electrons sitting somewhere stationary and they were hit with a photon, they would start moving. So momentum of the photon was transferred to an electron, as if the photon, light, was also a particle, like a billiard ball. And you can think, I guess we don't think about light as a billiard ball, but it behaved like that. Vis-a-vis electrons or other small particles, it could basically change the direction of the motion of an electron. Okay, that's the Compton effect. Atomic, I mentioned the Niels Bohr atomic absorption emission spectra. Double slit experiment is something that you probably, if you took first year physics, you would do diffraction grating, double slit experiments in optics. You basically shine light through an opening, single slit, double slit, diffraction grating, and see the whole spectrum of light, and you see the diffraction pattern on the screen. That was known for, what, more than 200 years, maybe more. Famous experiments of Young in Scotland with diffraction grating. So this was done now on particles, electrons and neutrons and protons, and you see the same diffraction patterns as for light, which showed you the opposite, that particles can be like waves. So a bunch of electrons, and this is again a philosophical conundrum, because if you really understand what's going on, then you start questioning your sanity. Namely, if you, the bottom line is this: if you have an electron which is ejected from some electrode towards another one, and there's the screen here. In order to see a diffraction pattern on the other side, like this, and this is a particle, think about a ping pong ball, and to explain this you have to say that this electron went through both. It's like if there were two doors here and I'm leaving in about half an hour, I go through both doors at the same time. And then you question your sanity. Are you crazy? It cannot be done. Well, it has been done for particles, right? Electrons, protons, neutrons, they do that. They behave like they split up into two pieces and then they reconstitute at the other end and form the diffraction pattern. So that's the duality again. Particles behaving like waves. Waves behaving like particles. In other words, it's the same thing. And what is it? We'll come to it. Double slit experiments. And then this was very interesting. And I forgot one more important example of macroscopic room temperature quantum effect. This is Stern-Gerlach experiment in which magnetic particles were flying basically in the presence of a magnetic field gradient, and they were splitting into two beams. And the explanation required something very original, namely the introduction of a new property of matter never before known to man, called spin. All particles, like electrons and protons, have spin, in addition to mass, charge, and momentum if they move. But spin has no classical equivalent. Well, like, angular momentum is kind of, if things move around, they have an angular momentum like a bicycle wheel. But an electron doesn't have to spin, it doesn't have to rotate, although we can think about it as rotating around its own axis, but it's only kind of Fuhrman's analogy. It always has spin. Its property, which is manifested when you apply a magnetic field, it will either be along the field or in the opposite direction. And so that's where the analogy with angular momentum breaks down, because spin can only be up or down, cannot be sideways. Okay, so spin of electron is spin 1/2. We'll come back to it later because it brings more mysteries of Mother Nature than we suspected. And therefore, it can only be plus 1/2 or minus 1/2 when you want to measure it. Why is this important? Because you played with magnets when you were in kindergarten maybe, or at home with some toys. Yeah? All of you know magnets, little magnets, fridge magnets. So magnetism is a phenomenon which is based on the existence of spin. There is no magnetism without spin. We didn't know it. Ancient Greeks, Egyptians, Romans used magnets, magnetic needle, compass, right? Without knowing that this is a quantum phenomenon. Because spin is a quantum property. There is no magnetism. It's mathematically proven by Van Leeuwen in 1920 or so, that magnetism does not exist without spin. If there was no spin, you would not have magnetism, ferromagnet. So the upshot of this is that magnetism is a quantum property of matter, some type of matter, iron oxide, so on, which is not only macroscopic, because you can make a big magnet, a huge magnet, but also exists at room temperatures and higher. So it's a quantum macroscopic high temperature property. Okay. And to explain, of course, the presence of Wolfgang Pauli, another crazy physicist, who, well, that's another anecdote for another day maybe, but he got Nobel Prize, of course, and married a cabaret dancer for 2 months, and then he said, no, I don't think we have anything to talk about. So sometimes, somebody said that to be a genius you have to be out of balance in some category, right? So somewhat crazy, and I think some of these people were really borderline crazy, and Pauli was. Okay, so this is a summary of going back to duality. Maybe I'll just skip it in the interest of time. The only thing that I want to say is that really, when you look at different aspects of waves, reflection, refraction, interference, diffraction, polarization, the only thing that that was completely impossible to explain classically was the photoelectric effect. So you needed quantum concepts to it. Okay, so this was the Broglie associated. So now the flip side, we talked about these electrons becoming waves, and he determined the wavelength of any particle. And this is kind of intriguing, and simply said that the wavelength of any object with mass, let's say, is given by this formula. Lambda is the wavelength, inversely proportional to momentum. So momentum is mass times velocity, back to Newton, right? And you can calculate your own wavelength if you want, as a homework assignment. You know, this is the Planck constant H, so it's 6.6 times 10 to the minus 34th joule seconds. And if try to think about yourself as a particle moving at what's the highest speed you can run at? 10 seconds per 100 meter dash, right? 100 meters in 10 seconds would be pretty good. Let's say that's the highest for all normal human beings. That would be our maximum momentum. The mass, I don't know, whatever it is, 70 kilograms or 60 or 80. Do the math, multiplication, then you'll get the wavelength of you as a wave. Do you have any idea what this might be? We can do this exercise here. So, if let's say I'm going to make life very simple here, and I assume that we all weigh 100 kilograms, right? And we can run at 10 meters per second, so that'll be 1,000. That's our momentum, 1,000 kilogram meters per second, and this is joule seconds. So you get your wavelength, or Usain Bolt's wave, but he's not 100, I'm sure, would be something like 6 times 10 to the minus 37 meters. 10 to the minus 37 meters, you think is, what is this? Is it even measurable? No, it's nothing. In other words, when you take it to microscopic objects, quantum mechanics completely is useless. In this kind of thing, the wavelength will be so close to your body that you can't see any difference between the quantum wave function and your own size. Okay, so but it makes a difference for electrons, protons, larger particles, even atoms, molecules. Okay, so we talked about this. This was an example, which I'll skip. And finally, the third most important example of this is actually a friend of mine. I borrowed this slide. Ernest Rutherford, who was a New Zealander with, he spent I think 5 years at McGill in Montreal. So he came up with the atomic model of the atom, which at that time was, okay, not really well known, but you have the nucleus and the electrons, and that gave rise to Niels Bohr's solar model of the atom. So it looks a bit already like a planetary system, electrons moving in orbits around the nucleus. Rutherford's contribution was the fact that there's a positive charge in the nucleus and negative charge outside due to electrons. But the enigma that classical physics could not solve was that if you have positive charges and negative charges, they attract. Right? So that this would collapse because there's no explanation why this is not collapsing to a point. And for this you need to add a quantization principle. That electrons are stable only on quasi-circular orbits. They move around the nucleus and maintain the stationary orbits, and the orbits actually are very, very discrete. Each orbit carries a particular energy with it, and sorry, but transitions between orbits correspond to emission or absorption of electromagnetic radiation, hence the spectra. Okay, so this is how the atomic model is confirmed by spectral lines and spectral line assignments. And by the way, this today is the basis for almost everything that we do in terms of spectral analysis from stars, the composition of matter in distant stars, galaxies. You analyze the spectrum coming to Earth from these, and therefore you identify which atoms are present. Is there carbon, is there water, Mars, and so on. All the way to the analysis of chemical composition of toxic waste, or microanalyses of metabolites. The same concept of obtaining spectra that correspond to transitions between energy levels of electrons in different atomic configurations. So spectroscopy, I mean, we owe a lot to spectroscopy. Right? You can measure trace elements of anything in toxic effluent. You can find polluters and so on and so forth. Composition of chemical compounds. That's the atomic model. And so these were the Niels Bohr and Heisenberg added something that Niels Bohr didn't know, because Niels Bohr was still on this sort of old mental plane that you can precisely determine the positions and momenta, but that's not so. You need to add Heisenberg uncertainty principle to do that. So this is the Heisenberg uncertainty principle for position momentum. The absolute upper limit on our precision in determining the two is the product of uncertainty in position and the product in the uncertainty of momentum, mass times velocity, is Planck constant divided by 4 pi. That also applies to other properties. I mentioned to you energy and time. You cannot simultaneously know the time and the energy. And you cannot simultaneously know the two components of angular momentum or spin. Okay, and now I will spend the last 10 minutes of this talk just wrapping things together. Going back to 1927, because in 1927 the Solvay conference codified or formalized quantum mechanics and ended up with 4 postulates of quantum mechanics. And this is something that maybe you should try and take home with you, because these postulates is like the foundations of our knowledge, just like Newton's mechanics has some, Newton's law, first, second, and third law. We have 4 postulates of quantum mechanics. The first postulate of quantum mechanics is that microscopic systems, the quantum systems, are described by wave functions or state functions. Abstract mathematical quantities. Wave function is a complex function, let's call it psi, which depends on space, x, y, z, and time, and may also have some other variables like spin and other ones if you go deeper. But let's say position and time for most cases. Complex and it contains all available information or accessible information about the system. And there's a lot of interesting debate, philosophical debate in the last century about there may be some hidden variables, hidden information we have no access to. And some people try to put this in and say, well, if we knew this information, then we could go back to Laplace and predict the future and blah, blah, blah. But so far there's no evidence that there's some hidden information, hidden variables. Einstein actually, in his last years of life, he rejected quantum mechanics, by the way. He didn't believe in it. And he was seeking these hidden variables and thought that if we found hidden variables, we'd be able to bring quantum mechanics back to classical type of thing. But so far, there's no evidence of this. Okay, so state function, a wave function, and it's actually has specific mathematical properties. I don't want to spend time just discussing it. Not anything. It has to, basically when you integrate it over all space, it has to be 1. So it's normalized. Which means that the probability of finding a particle somewhere in the universe is 1. It is there, but you don't know where. Right? If it was less than 1, you would say, well, it may be escaping somewhere from the universe in a black hole or wormhole or something. But no, it has to add up to 1. In other words, it's a probability distribution function when you square it. Okay, this is the second, by the way. I just linked to the second postulate. The first is wave function describes all the information about the system. The second is that the meaning, and that's from the Copenhagen situation, of the wave function is when you square it, you get the probability of the system or particle being somewhere in space and time. So the square of this function gives you the probability distribution. Just like if you were to distribute the population of Canada, you know, you don't know where you are, let's say, or your friend is currently, but you know that the probability is the highest that somebody's in Toronto because this is the biggest center. That's the probability distribution. And then the second largest will be Montreal and Vancouver and somewhere else. But the probability that somebody's in Tactayata is very small, or somewhere in the, you know, in the Bering Strait on an ice floe. That's basically what this is. The square of the wave function is the probability distribution of something being somewhere and sometime. Okay, so now this is maybe the hardest postulate, which is really, you have to believe it, but that's what it is. In classical physics, you have physical measurable quantities, physical quantities. So the quantity could be position, energy, momentum, angular momentum, what else? You can have some temperature or some other properties. In quantum mechanics, you replace all of these with so-called Hermitian operators. So these are actual operators, mean operations, mathematical operations acting on a function, returning another function. I cannot make it any simpler, unfortunately. So for example, position is a position operator. And you put a hat on it to denote this is not a variable, but an operator. An operator acting on a function returns the value of that function, eigenvalue. Momentum is a partial derivative with respect to position in quantum mechanics. It's not m times v. If you remember first year physics, you say momentum is mass times velocity, right? No, in quantum mechanics it's not mass times velocity, it's a partial derivative. That's the x component of momentum. Partial derivative with respect to x, and by the way, multiplied by the Planck constant divided by 2 pi and I, square root of -1. And honestly, I don't have the time to explain why there is an h and an I, but. And finally, the energy, with the most important physical property ever invented or defined, is this. This is the kinetic energy, so the momentum operator squared divided by twice the mass of the system, plus the potential energy, whatever the potential may be. So, again, I'm not asking you to remember these equations, and I will stop in just 2 minutes, because we have the, oh my gosh, something got cut off. But I'll find it, it's strange. The fourth postulate is basically the introduction of the Schrödinger equation, replacing Newton's equation of motion, or Hamilton's, or Lagrangian. And so let's see, I should have it somewhere else. Oh, it's almost here. Not really in this form, but okay. Yeah, okay, so I can just write it down. So this is the most important equation of all of physics, the Schrödinger equation. And it basically tells you how the wave function of the state of the system depends on time, or evolves. So, so that's a partial differential equation. This is an operator, so this will have 3 spatial derivatives, second derivatives. And this is the time derivative. So, don't freak out. When I took my first quantum physics course, my instructor told me, don't think about it, just solve the equation. So unfortunately, that's more or less what it is. And there's many arguments why it is so, and proofs that this is correct. But that replaces Newton's equations in the micro world of quantum particles. And okay, that's the guy who's responsible for it, Schrödinger. Got the Nobel Prize in 1930. And this is very important, a very important date, and I'll just spend 1 minute about him. Austrian physicist. 1933, if you know history, was a very important year in Europe. Hitler came to power, and just a few years, 2 years later, I think they annexed Austria in the so-called Anschluss. Erwin Schrödinger was not Jewish, his wife was, and they escaped to Ireland. He spent the Second World War in Ireland with his wife, and so he came up with the wave function and the Schrödinger equation. He came up with the Schrödinger equation spending 2 weeks on ski holidays in Switzerland, which is actually a good message for everybody to spend some time skiing, especially spring skiing. And probably most importantly for this crowd, in 1943 or 44, before the Second World War ended, he wrote a book called What is Life? And this is the most important book that started a conversation between physics and biology. Basically, he set the tone for this entire dialogue of what physics can do for biology and what is enigmatic in biology to physicists. And the most enigmatic thing that he came up with is entropy. Living systems reduce entropy. They become organized or ordered, as opposed to physical systems which get more and more disorganized and disordered, left to themselves. So this book is very slim and maybe 150 pages long. You can get it on Amazon probably for $5 or 10. I highly recommend because it's still an important perspective on biology from a physicist's point of view and one of the greatest geniuses. So that's basically the end of the first lecture. I hope you at least gained a little bit of a perspective on where quantum biology may be coming from. And next Tuesday, we'll actually talk about quantum biology itself. So, any questions? Yes?
I have 3 questions.
Sure.
Well, back to the work function, it's probably like a really basic question, but like, so photons have energy and then they release electrons. So do the electrons have less energy than the photons' energy?
Well, they are bound to the surface of the metal. So you have to free them because they are attracted to the negative potential, core potential of the metallic ions. Positive potential, sorry, of the metallic ions, they are themselves negative. So that's electrostatically attracted to the nuclei of the metal, right? So in order to overcome it, you have to give them a kick. And photons provide that if they have enough energy. But it so happens that this energy gap is somewhere around, I don't remember, 3-4 electron volts, maybe something like that, which is exactly the, luckily this is in the visible, so we can use visible light to, I don't remember what surface of which metal they used in this experiment, but it's visible. So for red light, it was not enough energy, but for blue light, it was. And so that's the work function, meaning of the work function. Basically, attraction of electrons to core potential of the nuclei. And you said more or less. Well, it has to be, that energy of the photon has to be at least as much as the attractive energy to the nuclei. If it's more, then it'll not only free them, but give them some kinetic energy, so velocity. They will start moving at some initial speed. All right? That was a very important experiment, and we'll come back to it on Tuesday from the photosynthesis point of view, because in photosynthesis we have actually something very, very similar. Photons striking the surface, molecular surface of chlorophyll and giving energy to electrons without causing conduction-like process, but exciton transfer, so the energy gets funneled and collected in collection centers. So that's a very similar, that's why it's important to understand the photoelectric effect from the point of view of photosynthesis. And I understand that these concepts, it took 100 years, and even the most, actually Richard Feynman's credited with saying that if you think you understand quantum mechanics, you're either lying or you're an idiot. So don't feel bad, okay?
I just have.
Yeah, sure.
Sorry. It's on the same topic. So, light, like every material has like an absorption spectra. Is that wavelength always less than its emission spectra?
Most of the time, but I don't know if it's, sometimes it's almost the same. I don't know if there's, yeah, so absorption spectra allow you to excite an electron to a higher energy level. We'll maybe talk a little bit about this. And emission spectra, when it falls down on the ground, so-called ground state, or the lowest energy state, or some less excited state. Sometimes it's a multi-step process, but cascading down to the bottom, right? But sometimes you go straight down to the bottom.
So for the photoelectric effect, let's say if we had less than the work function's energy, would it release like a photon then instead of electron?
Oh, no, well, that's a good question. I'm not quite sure. For metals, it would not be so now, because for metals, you have an electron C. You need to have sharp energy levels. Metals have bands, so it's a bit more complicated. It's in this case, it's just reflected. It's not.
Oh right. And my last question is like you have observer and some effect on the quantum level.
Yes.
And like that always like affects the system.
Yes.
Can we ever like predict what our effect on the system would be? For example, we observe it with like a photon. We know the photon.
So you want to reverse engineer it?
Obviously, this is like theoretical.
Well, now you have to make an assumption of what the state was, but you don't know what it was, so it could be.
We know what happened after, right? And we know how much energy a photon has, but
Yes, you do. I see where you're going with this. I'm not quite sure if you can actually. So you're kind of asking me whether you could, from this information, figure out what was actually the state initially. I think to some degree, I'm not quite sure if you can really make it. According to Heisenberg, you cannot precisely determine anyway. So I kind of take it as my guiding principle, but I don't know how you where this would be manifested. Yeah, that's a good question. Let me come back to you next week.
oh, it's fine. I was just.
That's a tough one.
Any other questions? Okay, great, thank you.